Hi, everyone. Welcome to today's Alaska Collaborative on Health and the Environment webinar entitled Pollution and the Planet, Perspectives on Being Outside the Safe Operating Space with Dr. Sarah Cornell. I'm your host, as usual, Nick Reardon, and I'm calling in from Alaska Community Action on Toxics office here in Anchorage, Alaska. And we're on the traditional and unceded lands of the Dena'ina people. So my coworkers and I continue to be grateful to past and present stewards of this place we call home. For those of you new to the webinar series, the Alaska Collaborative on Health and the Environment is a regional partner of a national collaborative on health and the environment, which we often abbreviate CHE and pronounce CHE. So CHE Alaska, and there's other CHE partners. We're working together to advance knowledge and action related to links between human health and environmental factors. When organizing these webinars, we try our best to select issues that are of importance to Alaskans. So considering how our state, how the Arctic and Arctic communities are impacted and the solutions that make sense for us. So with that in mind, I do welcome you, our audience, to reach out with suggestions. What environmental health issues and concerns are important to you? What would you like to learn more about? So feel free to share ideas, requests in the chat, ideas for speakers and topics. You can contact us directly by email or phone. We maintain a list of topics and recordings of past CHE Alaska teleconferences as well from the last 15 years. And so I invite you to take a look at that and for CHE Alaska and CHE National. So that's akaction.org and healthandenvironment.org to check those out. And a special thanks, as always, to Alaska's state legislators and their staff who could join us today. We're always really appreciative of you taking the time to tune in and for your concern about your constituents' health. Without further delay, we're very grateful to be joined today by Dr. Sarah Cornell. She's a global environmental change scientist, as well as an associate professor at Stockholm University, and works as a principal researcher at the Stockholm Resilience Centre there. And so in this role, she leads a research group that seeks to integrate planet scale perspectives into social ecological systems approaches for dealing with risks, resource use, and really responses to today's environmental challenges. So welcome again, Dr. Cornell. Thanks so much for joining us. And yeah, feel free to share your screen and I'll turn it over to you.
Thank you. Thank you so very much. Can you all see? Excellent. I, first of all, need to actually acknowledge the logos in the corners of my slide. I always forget to acknowledge our funders. So some of this research and the research group that I lead is funded through the European Commission and the European Research Council. So that duty is now out of my way. I'm so grateful for this opportunity to speak with you, but I need to give my disclaimers too. I'm really not at all an expert on health, but I do understand things about the environment. And you'll see from my discussion today that I have a very large scale, long-term view of environmental processes and also of our place as human beings in this planet Earth. So the task today is to talk a little bit about pollution and the planet. And I don't often use the language of planetary health, but really maybe that's a useful metaphor for you to hold on to as we through this session. So it really goes without saying that people are changing the global environment. The world is changing very fast around us. And it has become a topic for global change research, really for many decades now. So this is my first question for us. What do global change scientists think about the ways that human activities are changing the whole planet right now? I'm an Earth system scientist, and I'm going to take a few minutes just to sort of explain what that is. To start with, we understand the planet as a physical planet. A lot of the focus has gone on understanding climate change, and of course, the climate changes that are caused by human activities. And the physical science of climate change really focuses on understanding the wet and windy parts of the planet, understanding how atmospheric processes are changing and how heat and energy are transferred through ocean circulation. And we can use that science pretty much for any planet that has an atmosphere, to be honest, but this planet is special. It's a living planet, and life and the physical environment really have co-evolved. It's a defining characteristic of life that it will try to exploit its physical environment, and in exploiting it, it changes its environment. And that's true for bacteria and fungus, and it's true probably for human beings too. And we can see the changes between life and the physical environment through chemistry, through my own field of research, which is biogeochemical flows, the ways that chemistry of life and its surroundings interact and interplay with each other at the global scale. I told you it's exciting. And of course, it's also a human planet. And we're in the situation right now where we're becoming so aware that people are kind of behaving like a particularly aggressive kind of life form in some ways. We're altering the biogeochemical processes of the Earth. We're changing the physical conditions. And of course, we're changing the webs of life itself, the ecosystems that we ourselves are part of. Now, piecing together this story of physical, ecological, and social change is the big task that we as global change scientists set ourselves. To do that, we have to piece together information from observations that we can either do in situ in particular locations. You see ecologists going out there catching butterflies or looking at slugs. We have to have that on the ground knowledge of what the consequences of our activities are. But we also use big data. Earth observations from space have played a really important part. We can do experiments at all scales, from laboratories actually up to, you might discover, you might consider the global changes that we are creating now as a planetary experiment, just one without a very good control experiment to fall back on. We bring together theory from all of these different areas of research, and we often combine them in quantitative computer models that help us not just to understand, but to some extent predict how the Earth system works. I've used this language of Earth system a couple of times, so I just want to be really clear what a systems approach means. Now, for anything to be considered a system, it kind of needs to have a structure. It needs to have components that are organized in some way together. Systems do things. To be a system rather than just a pile of bits, it needs to function in some way. And it needs to function in a kind of a characteristic behavior. So we would describe that as integration. The components act together in a way that let us recognize the system as a thing in itself, not just, again, as a pile of pieces. Now, when we bring this up to the scale of a planet, the really important thing is that when you change one component in the system, the effects kind of cascade all the way through the rest of the system. So even if you're far away in space or time, you will sense the change. Because all of the other components in the system will respond to that initial perturbation, that initial disturbance. And it's the responses of those other components that we would use, that we describe as regulating the overall system. So there you go. That's an introductory lecture to systems research without the quiz at the end. But I want to dig into Earth system science. And I always use this really rather messy and complicated diagram with my students. I teach a master's program called Challenges of the Anthropocene, and we'll talk about that in a bit as well. So this diagram is now about 40 years old. We call it the Bretherton diagram after the Bretherton report for the NASA Earth System Science Committee where the scientists involved kind of gathered together their knowledge from the different contributory parts to, it's like a wiring diagram for the Earth system, with all of the processes that matter at this planetary level over timescales of, let's say, centuries. And it's really important in our field of research because basically this wiring diagram is what is now included in Earth system models. Every little white square on the figure is something that required measurements or observations to be made. So that includes things like the flow of nitrogen between land and ocean, or the concentration of carbon dioxide in the atmosphere, quantities that we can measure. But oops, I went too fast. The important thing, I don't expect you really, I won't quiz you on this, but the important thing about the Bretherton diagram is that it shows the relationships and the processes that connect atmosphere, ocean, land, and life itself. And of course, I'm a chemist, as I said before, so I'm particularly interested in the chemistry aspects of this system diagram. Another little bit still on semantics and terminology. I said that systems behave. In Earth system science, we talk about the external forcings, these perturbations that make the system change. Some of them will be really big things like major volcanic eruptions or changes in the solar radiation arriving here at planet Earth. But increasingly, we see human activities as having a disturbing effect on the system as a whole. Now, obviously, humans aren't exactly external, but they're external to our modeling approaches for Earth system science. And that's important when it comes to how we as scientists try to connect with society and communicate about environmental impacts and their consequences for people. Another important idea is the idea of feedbacks within the system. And you kind of have to trust me now because I put a big orange arrow over the feedback here. But just to give you one example, if we change the vegetation on land, it changes the chemistry of the atmosphere in ways that change the ways that clouds form or the ways that plants go through their process of evaporation and transpiration. That changes rain. And of course, that in turn goes back and changes what vegetation is possible. So a feedback is something where you end up with a strengthening effect, or in some contexts, a kind of balancing out effect that arises from the first disturbance. It intensifies the problem in this particular example. So we're in the situation now where we have a system understanding of the planet. We've got data and models that join all the pieces together. We know that human activities are pushing the system in new ways, roughly of the same kind of magnitude as major volcanoes or solar flare events. And we are changing the feedbacks within the system. The reason we care about this as human beings is, or as scientists first, is because when you change the feedbacks in the system, you make all of the system's responses less predictable. So we move away from having a system that we have got really well characterized, and we're turning it into a system where we do not necessarily know how the changes will play out or where in the world they will play out. So this, of course, is something that connects you in Alaska with me and my lifestyle here in Sweden. So a little breathing pause. What's the state of a planet? How can we talk about a system state for a whole planet? But as I've sort of hinted, one of the ways we do that is to look over different timescales and different time frames. And this is a diagram, a graph that I've actually taken from Wikipedia because I love it. And the nice thing about Wikipedia is that you can see how the diagram has developed over time and how, I can't remember what Gareth Fergus, I can't remember his first name, I'm really sorry. What he's done over the last decade or so, piecing together data, geological data from many different timeframes. So each of the panels, this picture needs a bit of explaining. Each of the panels in the rather messy graph is a kind of telescoped window on Earth history. And the further you move over from 500 million years ago on my left-hand side to the present, the zero on the right-hand side, the more you kind of imagine that time has been stretched out. Obviously, we don't have so much detail in the deep Earth history as we do in the contemporary context. But one of the most important things for the world that we live in now is this recent-ish behavior in Earth history that for the last million years or so, the whole Earth system has been sort of moving between ice ages that are very cold and warmer periods that we call interglacials in between the ice ages. And this behavior has been really quite we can see it in ice core records and in ocean sediments and many, many different kinds of data. And in a way, the basic condition of Earth at the moment is this sort of cycling between ice ages and warm periods. We're in the middle of, well, not necessarily in the middle anymore. We are currently in an interglacial period. It's not exceptionally warm. It's not exceptionally long lasting when you look over long Earth history. But the important thing is that it's our interglacial period. It's the last 10 or 12,000 years is really the time when everything that we regard as human civilization has happened. Human societies rely on stability and predictability. And that's true wherever in the world you are, whatever conditions you're experiencing and exposed to. And this interglacial period, the stability has meant that things like international trade, settlement and agriculture, even the building of, kind of big cities that we now regard as kind of normal. More than half of the world's people live in urban environments now. All of that has really happened in a relatively narrow time in Earth's history, relying on this stability. Oops, I've already jumped through to this slide. Yes, you can see that for the past 10,000 years or so, Earth's climate has been stable. This is a climate signal, a climate temperature graph, but actually Earth's ecosystems have been comparatively stable too. And again, I want you to hold in mind this idea that the physical and the living parts of the planet kind of are like two sides of a very, I don't want to be coins, I don't want to bring money into this story. They are the same thing. In a living planet, life is climate, and climate is life. And right now we're in the situation that we know that temperatures are rising because of human activities. We know that many of the world's ecosystems, the environments that we ourselves are part of, are not well adapted to these kinds of climate conditions. They haven't seen them before. And we also know that if we don't do something about resource use and climate, particularly climate change right now, we're pushing the temperature of the planet warmer and warmer into conditions that really we have to go into deep Earth history to find anything that looks the same in the physical context. And that takes us way outside of anything that looks the same in the ecological context. I've got another fun graph figure diagram that is equally complicated to explain. This is a representation of the tree of life, starting in the middle of the graph at the bottom where it says millions of years ago. It's actually 4 billion years ago that this evolutionary tree has been mapped out. And it shows how over time, Earth's life has become more diverse, has become richer. And it also has these sort of extraordinary holes in the web of life. Those are the things that scientists would describe as mass extinctions. And there have been many reasons for those extinctions, usually something enormous falling in from space or a massive mega volcanic eruption when Earth was still hot and young. One important thing about looking into Earth's part as a living planet is that each one of these mass extinctions, obviously we can't bring life back once it's been destroyed. But some of the functions of life, again, this is why chemistry is so important. It lets us see how the biogeochemical flows change over time. The functions of life can be restored, and life up till now has continued to diversify and exploit the planet. It takes 10 million years for systems to rebound chemically and ecologically from these mass extinctions, plus or minus quite a large number of years as well. But we know the consequences of the extinctions that human activities are causing now are going to take a very long time to play out. We won't see the consequences necessarily of these extinctions that are already happening in our lifetimes. So one of the challenges for our system science is to make people think about the long now, not just the very local, very immediate effects of our human activities. Not only to think at the level of an organism, but to really think about the planetary organism as well. So because of that, I've given you two indicators. The temperature of the Earth is changing and the livingness of the Earth is changing. And the geologists of the world, particularly the stratigraphers, the people who make the categories of Earth history, have been debating really for the last 10 years or so, this idea of whether we need to label the current conditions of planet Earth with a new name. We have been in the Holocene these last 10,000 years, and the debate is about whether we should be relabeling this new phase, the Anthropocene, the era of human control of the planet. Now, obviously, there's a lot of debates about any of those words. Human, which humans? And at the moment, most of the impact has been done by the rich, the wealthy, and people in the global north. So there's issues around the power, there's issues around the presumption of control, and I'll come back to that later. But the important thing, and the thing that there's no argument about, is that scientists can observe and detect the changes, both in the physical environment and the living environment. And we know that the changes that have happened so far, many of those changes in my lifetime, are now enough to leave a pervasive signature in the geological record. And it's in this context that a group of Earth system scientists got together and said, okay, now how much change is too much? And actually, they weren't asked the question in terms of how much change is too much for people. They were asking the question of how much change is too much in the sense of this sort of demarcation of the stable Holocene from an unstable and actually much less predictable future world. So the first thing I will really emphasize is that the planetary boundaries framework is a biophysical framework for understanding the many ways that planetary change is happening. It was a scientific agenda in the first case. But to start with, one of the most important things is the recognition that today's human-driven changes are bigger in magnitude and faster in rate than many changes that have been seen in Earth's geological past. I mentioned that many of these changes have happened in my lifetime. We also know that today's ecosystems and human societies are very much, we developed in the conditions of the relatively stable Holocene baseline. So one of the few things we can say with certainty is those conditions are kind of good for people and the ecosystems on which we depend. We don't know very much about the other conditions. We also, okay, this is the normative position of the framework, that really global sustainability means staying within this biophysically characterized safe operating space for humanity. I've already said that we can't actually stay within, in the sense that we can't unextinctify lost species, or there's no way on Earth of unacidifying the ocean that we've already contributed to. The chemical changes have happened and we can't reverse them. But we can certainly do something about reducing the pressures on those risks. So anyway, about a decade ago, a group of international group of Earth system scientists and other kinds of researchers, including policy scientists, got together and they said, okay, how do we bring our science into an understanding of planetary conditions for global sustainability? And they flagged climate change, biodiversity loss, and biogeochemical changes as already showing the signs of Earth system disturbance. like I've just mentioned, that sort of, okay, we'll go back and look at that picture. It's often shown with this kind of radar plot visualization. So it's useful to think of it as a dashboard of changes to Earth system behavior. It's precautionary in the sense that we're moving into conditions where we cannot predict with certainty what the outcomes will be. And it's definitely a planetary perspective, not a local perspective. We find it useful to use it in combination with local impact indicators. And people are interested in using it. I work with people in business and in policy, particularly at the European level. And each one of those little red alerts on the figure, even though the dashboard shows them as separate, if you go back and think about the Earth system mess diagram that I showed, they're interesting pressures and they're building up fast. So about 6 years ago, several of us got together to update the framework. And at that stage, we also realized that land system change was demonstrably disturbing the way the planet functions. So 4 of the 9 boundaries had been overstepped. And now, just in the last the last year really, we're in the situation where instead of having 3 out of 9 boundaries that are reasons for concern, we now have just 3 that are not. So 2 papers came out earlier this year, one on water, particularly the water that moves through vegetation, what we call green water, and for chemical pollution, which is why I'm talking with you now. In the chemical pollution paper, we obviously realize that there's no single indicator or one single variable that captures all of the chemical functions of everything on Earth. We have opted instead to think about the impact pathway, everything from the production of chemicals and the resource use that's required for that, through to the environmental consequences when you realize that chemicals are transported all around the world, through the oceans, through the atmosphere, and actually through life itself. A lot of these substances that we're most concerned about bioaccumulate. They affect the organisms, including humans, from the inside out. One of the big problems we have with chemical pollution is that obviously we don't have natural variability, unlike climate change, where I showed you the wiggles in the deep past, or biodiversity, where we know things about species formation and species extinction. There's really nothing in the world that we can use as a simple precedent to say how much chemical pollution is too much. A really literal thing would say, if we're making things that we know are designed to interfere with physical processes or living processes, then basically the number should be 0. Policy people don't like that very much. We usually end up having to sort of find some kind of critical load or some kind of a justification. But when we take a planetary perspective, we can see that chemicals are causing physical, biogeochemical, and ecological changes. Indirectly and directly, they affect climate stability. So we know about greenhouse gases, we know about ozone depleting substances. They change the planet at the planetary scale. And we know about the sort of creeping, insidious ecological consequences. Again, I've mentioned bioaccumulating substances, but also things that just change the web of life, knocking out one particular species or species groups. DDT in the 1960s and 70s is a really important example here, because it obviously was intended to kill insects, but it also destroyed bird life, not by killing the birds, but by meaning that their breeding success was much reduced because of eggshell thickness. So this is an important thing. When we think about planetary scale impacts of novel substances, we need to think all the way down the scales, from the planet through to the kinds of things that humans can recognize as species, like trees or birds or fish or whatever it might be, beluga, and below that as well, because of course all of life is part of this profoundly interconnected web of life. We don't often think about the effects on fungus or the little tiny bacteria in root nodules, and chemicals are affecting those. We don't often think about the effects of microplastics in the ocean and what they might do for plankton. And we need to start thinking about all of those things. This whole paper, led by Lynn Persson, a colleague of ours, really points to the fact that if we think about chemical pollution, both from a planet perspective and from the tiniest levels of life, the balance of evidence is that we are already beyond what we can regard as safe at the planetary scale for novel entities like synthetic chemical substances. So we're at this situation where I've been talking very much in the scientific abstract about planet scale problems, but of course these are also people scale challenges. When the Planetary Boundaries article first came out in 2009, the one that presented the framework, a social scientist who was at the time the head of the Netherlands Environmental Assessment Agency said, yeah, that's great, scientists. Great to give us all these big numbers. The problem is the idea that the planet has a cockpit, and in the cockpit, we can change course. So this idea of the kind of the radar plot telling the world where to go. And Martin Heyer said, the planet doesn't work like that. So this is one of the questions that I ask myself in all of my everyday work. I think we do need top-down planet-level analysis to help us put today's activities into context. But I also agree completely that the planet doesn't work like that. Just giving policymakers big numbers doesn't actually mean that the world will change. We see that with 2 degrees or 1.5 degrees for climate, so, hasn't radically transformed the climate pathway for the world as a whole. Or maybe it has, but not in the ways that it was intended. But having said that there's nobody in the cockpit, there are lots of forums bringing together the governments of different nations or bringing together heads of business who are now extremely influential in this context, for better and worse at the same time. The UN Environment Assembly has recently agreed that they will develop a global treaty on plastic pollution. Now, obviously, plastic is an interesting thing because it's visible. We can see it, we can count it. It goes into the environment in big chunks and it breaks down into invisible chunks. And for the longest time, people thought plastic was safe because big plastic doesn't hurt people. And people thought microplastic was essentially invisible because it wasn't visible. People weren't looking for it. But just in the last few years, the more we look, the more we find. The more we explore its impacts, the more we see that the impacts are more severe than we imagined. So this has been a very, very, very fast turnaround from an issue that used to be for kind of crazy hippies who cared about, surf water quality and turtles, to something that is a huge political and economic issue right now. We might come back and ask some questions on that. Another recent report, this time from last year, is again a report from the UN Environment Programme, where they raise chemical pollution right up to the highest level of policy importance. They describe it as a planetary emergency at the same scale and the same importance as climate change and biodiversity loss. So that again is sort of saying pollution is not just a matter for a local environment or for a national decision maker, but in a globalized world with globalized trade, we kind of need globalized responses as well. Now, one of the big challenges of my everyday research is how to go from understanding the world as a biophysical world, as a world where climate and life kind of co-evolve and shape each other, to a world where we can actually deal with the issues of environmental justice and fair responses to these problems. In a lot of our work, we break it down to 3 steps, and we actually have a very specific sequence for the 3 steps, not least because we start with the biophysical science. But in a way, the physical environment isn't negotiable. It's an important actor that shapes our everyday choices, but you can't actually tell water not to wet its surroundings. You can't tell vegetation to behave in different ways. It's not part of the political negotiation process. So we think that there is something quite important about bringing the best of our knowledge. And that isn't just scientific knowledge, but scientific knowledge has played an important part so far into these policy debates, these translation debates for the chemical pollution problem. Then we look at the social and economic dynamics. And I kind of hinted at this, that global trade means that a problem doesn't stay local anymore. And we need to think about the complex web and network of global trade in just the same way as we, and of course, not just the visible web of trade, but the kind of the social consequences of production and consumption. Plastic pollution goes all around the world, regardless of where it was used, for example. So if we think about the network or the web of societies and the ways that we use resources and the ways that we dispose of waste, then that's a different layer. It messes up a perfectly good physical model. So we need to give it special attention. And then, of course, it isn't just about the quantity. This, again, is where I agree with Martin Heyer. A planetary response shouldn't just be a quantitative response. We need to bring the quality of life, these issues about fairness, the distribution of benefits and unwanted consequences as well. And of course, that brings us into the domain of politics. And traditionally, scientists have wanted to sort of be separate from politics. So this is a new learning experience for many of us in this environmental field. And for me, this is also part of the reason why I think it's so important to engage in discussions like the ones you have, where we can, some of these things don't have a magic fix. The only way to make sense of them and to navigate the predicaments that we're in is through dialogue. And then I bring it down to the very level, the level of very personal and individual action. When we think about planetary changes, there are things that we as people can actually do. And so this is my own little checklist. Obviously, it's got loads and loads of ifs and buts and thens inside it. But the more I understand about planetary change, the more I think it's vitally important that we act on climate and waste. And like everybody says, nobody can sort of make radical transformations overnight without major disruption and discomfort. Some of that may well be needed as well, but we know what we need to do. We can reduce what we do and how much we do it. We can reuse the resources we already have. We can ensure that things can be recycled or regenerated as much as possible. But the important thing is to do it in that order. Reduce first, then worry about uses and reuses next. As much as possible, we should be thinking about protecting the livingness of the planet at all scales. If all you've got is a balcony, make sure that your balcony isn't a life-destroying balcony. And if at all possible, see if you can get involved in ecological regeneration. And the other one is the mindset issue. And I have, for most of my career, have actually tried very hard to avoid talking about feelings in my everyday work. Again, it's we somehow, as scientists, internalize this view that it's our job not just to be objective about our objects of study, but somehow unfeeling about the consequences in which we work. And there's quite a few of us to sort of reopen that discussion, thinking about our responsibility. In that context, I mean, just as you, Nick, as you opened the session, recognizing that the place you're in has a history, a heritage, and meaning associated with it that goes beyond your own lived experience. That awareness of our place in the world also needs to happen at all scales, from our literal footprints up to the planetary. And for us, I mean, one of the issues that I've learned so much in the last 10 years that I've lived in Sweden at the Stockholm Resilience Centre, one of the things that connects all of our work is this recognition that the social and the ecological are embedded in each other. I'm coming to terms with the language of interbeing. It's a very hard, almost metaphysical thing to make sense of for those of us who are trained as scientists, not thinking like that. But the habit of being much more aware of the ways that our choices affect people and life far away, not just in distance, but also in time, is an important habit for sustainability. So that is pretty much where I'm going to end. We've got nice time for questions and answers, and I see that there's plenty popping up in the questions and answers section already. Shall I stop sharing?
Thanks so much, Dr. Cornell. That's, yeah, you can close out of it.
I've done it.
You've done it. It's happened. Wonderful. Yeah, thank you for walking us through what is a very complex story, but I really appreciate the foundations you laid there. And yeah, I invite the audience here to pop in with our remaining time. Questions, comments. You can type them into the Q&A box or directly into the chat box. We'll field them as they pop up. I know the
first Q&A was a really simple one. Yes, I will share the slides. I intended to do it beforehand, but didn't. Oh, good. You've already had that answered. Fantastic. Lovely.
I was quite curious. I mean, you described how, in the case of novel entities, that there is no, geologic history or precedent for some of these chemicals and their interactions. Wondering, how do you set a boundary on, and could you elaborate on how you set a boundary on something that you don't understand? I mean, I'm generalizing, but
that's been the most extraordinary thing. Kind of a discussion where, right, another thing about that paper was we had people from different kinds of research perspectives. So we had ecotoxicologists, people who study the kind of effects on different kinds of organisms or on ecosystems, but usually they're thinking of ecosystems this big, kind of not planet scale. So they're looking at specific things like salt marshes or, some constrained thing that people recognize as an ecosystem. And we had life cycle impact assessment people involved in engineering. We had chemical engineers and sort of industrial chemists who are also interested in the production processes and safe processes or sustainable green chemistry and all of that kind of thing. And then we had a couple of people like me who are sort of trying to say, all right, let's think about not the chemistry itself, but the chemistry in terms of its interactions and relationships with the biophysical planet. So whenever you've got a different group of scientists together, you end up with a handful of different answers. The life cycle impact assessment people are actually very keen that we should find almost like a maximum tonnage or a maximum diversity of chemistry synthetic chemistry that can be done. My own feeling is that might be an interesting exercise, but societies are so ingenious that if you set something like that, a quantitative target, they'll game the system. And that's essentially what we've seen with all of the regulation that's been put in place for chemical pollution already. That kind of cat and mouse chase. We see it very, very explicitly here in Europe at the moment with a thing called the REACH regulation, which is intended to deal with the worst consequences of the worst kind of pollution. And, chemists are really smart. They'll just change a little bit and go, well, this one's not regulated, or we'll make just under the tonnage or kilogrammage that is needed. And actually, this is part of the reason why I think we're really struggling to be able to, again, I keep doing this with my hands, that kind of for every quantitative issue, we need to keep its system story attached to it. The qualitative story belongs alongside the quantification. So one of the problems we have with the planetary boundaries framework as when you think about individual boundaries, is very much that people focus on the number and forget the system story behind it. So it's a bit like the kind of the Buddhist story of, looking at the finger, not at the moon, or whatever. The bigger challenge is, how do we deal with a dynamic system, knowing that that the whole world is changing around us? So my response to this isn't so much that we should over quantify the boundary, but that we should take a lot more attention to this translation of the boundary. Is just, we know we're in the red. So now what do we do when we break it down into component challenges? We should be able to set time-limited targets for reducing environmental releases. And we should set time-limit targets for responding to the environmental pressures that we know already exist. Some of those things might be bans, and a ban is in effect a zero boundary. But some of them will be much more about making sure that our control and regulatory systems keep up with the monitoring and measurement and mitigation of the harms. Does that make sense? Oh, we've got some fabulous questions.
Yeah, feel free if you're seeing them and you want to dive in.
As you say, they appear in both places, don't they? Okay. I'm going to start quickly with Kimberly Garrett's question about, what advice do I give to scientists who want to push back against the normative expectations of apoliticization and this being unfeeling? My advice is also a plea for help and support. I think that one of the most important things is to network and support each other, and write about the experience. There are many organizations about scientific responsibility. And I mean, a lot of them have focused on climate action, but I think it is important to sort of explore, first of all, network with each other through some of these existing networks for concerned scientists or responsibility in science. But also, as much as possible, if there are professional organizations that you're part of. So for instance, I was a member of the Royal Society of Chemistry when I lived in England. You can raise the issues in those professional organizations, make it be a conversation that people actually have, make people uncomfortable and embarrassed for not acknowledging their political biases. Just because they don't say them doesn't mean they don't have them. So that's two answers, two advices, but I might come back to it. Thank you for making me think about it myself. The next question in the Q&A section, and I'm going to answer live because I can't type and talk simultaneously. Well, I can, but only in boring meetings, is this industry pushback regarding regulation. I think it's been extraordinary. There's a group of researchers actively looking to see how much is invested by industry in pushing back. Now, obviously, we need to do two things here. We need to accept that it takes time for industry and innovation to be able to cope with some of the problems, but we also need to call out the abuse of power when we see it. The plastic pollution example is fascinating to me, and I actually have a fantastic PhD colleague who's studying the plastic pollution problem right now. In fact, she's just recorded a TED talk, so watch out for Patti Villarubia. I'll write her name down later. And plastic really showed that civil society, so citizen action, political awareness, and actually business that wants to do good, business leaders who want to do good, have actually come together in really productive ways. And I think that that's exactly the three-legged monster that we kind of need to push along. So yeah, when Martin Heyer says there's nobody in the cockpit, basically there are lots of people in the cockpit pushing the buttons all at once. So this is part of the reason why I think dialogue becomes so important. These platforms and forums where truth can be spoken to power, and where politicians and scientists and business and citizens are kind of forced to listen to each other, not just to talk at each other. That seems to be effective. Now, the challenge is it effective? We know it's effective at local scale. The challenge is it also effective at planet scale? Then I'm going to switch over just very quickly to, a couple of fantastic questions in the chat. Otto Sanchez asks about global North countries supporting the sort of lower and middle income countries more effectively, so that solutions really do play out worldwide. I said I'm not a health expert. I'm very much also not a global governance expert. But I mean, I think one of the issues here is that people, that's part of the reason that I'm so interested in following this treaty for plastics. I mean, plastic is just one example of the whole problem. But when things reach that international multilateral agreement level, then mechanisms come into play about resourcing the transformations that are needed, and recognizing the kind of, in climate language, the common responsibility, but the differentiated responsibility that people have. And this is where history of overconsumption puts a bigger responsibility, perhaps, for the wealthy countries to invest more to deal with some of the problems. Now, yeah, I think that's a very big question. And I'm quite interested to find out what the answer from Otto would be as well. And I'm going to jump down to Kristin Schaffer's question about these 3 urgent global crises. I was fascinated that chemical pollution is seen as urgent and global, because right up until that report, it's always been seen as a problem for organisms or local ecosystems. I mean, unless it's really big, like transboundary air pollution. But to recognize that everyday pollution, the pollution of everyday goods, is also a global crisis, was just extraordinary. And I mean, yes, I do see them as, I've always been used to doing this with my hands, saying climate and biodiversity crisis are 2 sides of the same monster. And now I've got to find a third hand, because I do absolutely believe that chemical pollution is, okay, it's a hydra now, isn't it? The other head, or the other head on this monster. Chemical pollution is deeply locked into resource extraction that contributes to climate change. Chemical pollution, for better or what, even some of it is intended to destroy biodiversity, not doing it by accident. So, I mean, it would be lovely to sort of find the spaghetti plot of the many ways that these things interact. There's a project for my master's students, actually. Follow this space. My master's students will look at interacting challenges and come up with a pretty picture. What else do we have? Oh my goodness, more questions than I can answer in the time. What do I do, Nick? I can answer questions by email as well if they get downloaded and sent to me. I'd be more than happy to do that.
Yeah, I can
because these questions
that.
are fabulous. They make me think. I just want to jump in very quickly with Bob Petsolesi's question about the intersection of science, environment, and faith traditions, and again, the interconnectedness and public awareness. I actually haven't spoken about planetary processes at these intersections. Many years ago, I worked on coastal zone research. This was when I was still in England. And there were some wonderful discussions by the leaders of churches living in low-lying lands, the lands that were exposed to flood risk and coastal zone erosion. Yes, the Laudato Si is a wonderful document raising the conversation and connecting with science, particularly the science of climate change. But I think more and more, okay, there's two quick points I want to make here. One is these are dialogues that we would want to maintain. And, you know, in ways, they have, science and faith traditions have been presented as if they were polar, you know, kind of separate issues in separate worlds. And to many scientists, I would say, many scientists would regard themselves as atheist or agnostic at least. And so it takes a particular kind of humility and a particular kind of mutual curiosity, perhaps, to come into these conversations as interconnected humans. But yes, thank you very much for the question. And thank you for presenting it so positively. I will give it good thought about the planetary angle. Maybe I shall pause there. What else should I answer, Nick? I've got a couple of minutes. Timothy how would I pronounce that? Chisielski has asked the terrifying question about minimally regulated corporate extractive capitalism. And yeah. In some ways, this is a really challenging issue for me in a very specific sense, which is half of me, this half, believes that even the act of quantifying the complexity of the system is part of the tool of a corporate capitalist way of looking at the world. It reduces the world rather than expands and enriches it. And at the same time, it's my job, it's my training, and it's been my career for the last 25 years. So I think that the real challenge, and I think the wonderful thing about having a COVID lockdown for a couple of years, and I ought to just show you my view, being stuck in a shed with a view like that for a couple of years, is that I have been thinking and I have been listening in ways that I don't think I necessarily have had time to do long enough before. And that sense of being complicit in a world that has this tradition of a colonialist worldview, a colonialist ecology, to describe it using the words of Malcolm Ferdinand, if you want to, and there's another thing I'll write to you. It makes me worry about the way that we use our numbers. And again, that's part of the reason I think it's so vitally important to open dialogue, not just throw numbers at the system. What a heck of a lot of questions.
You're doing a wonderful job. I really appreciate it. I'm also noticing we're coming up on the hour as well. And I am happy to send along additional questions. Thanks for your generosity with your time, Dr. Cornell. I can compile anything that's remaining and send it your way for some feedback. There's a lot of appreciation coming in here. And I share the feeling.
I see that. Thank you so very much. I'm so grateful for this opportunity now. Oh, and questions are still coming in. So definitely send your questions and I'll sort of sit with a cup of tea and have a go at answering them.
Yeah, feel free to send questions to my email as well. It's nick.r@akaction.org. And Dr. Cornell, do you have any final thoughts to leave us with? I think we'll be left with lots of thoughts and lots of pondering from this regardless. I know myself.
I've put my email address in, but I also just need to warn you that I'm going on my summer vacation in 2 days' time, and I'm sure as heck not intending to open my email, but you can find me on LinkedIn too. Just thank you so much for this opportunity. It's always a bit strange doing a one-sided talk at people. So I am so very grateful for the whole range of questions that have touched on faith, belonging, capitalism, justice, all the things that motivate me to do the science that I do. Thank you.
Yeah, we all really appreciate it here at ACAT and from the audience. And I think this, many future listeners of this recording, this is an expansive topic, I think, for what's otherwise often, very environmental health focused themed webinar series. And so this is, I think this will add a lot to future conversations and discussions. So really appreciate it. Just a few final words from me. I will send out an email tomorrow with a link to the recording of this presentation. And I encourage you to share it with your colleagues out there. And I'll update the list of related resources on ACAT's webpage with a few things that popped up during the presentation. So yes, please send any additional questions or comments my direction. You can reach out by phone or email. Our number here is 907-222-7714. And again, it's nick.r@akaction.org. And I am not going on vacation, so you will be able to reach me. But I hope you have a wonderful trip, Dr. Cornell. And thanks again for your time and your expertise and the work you do. It's really appreciated.
Thank you.
Yeah. Bye for now, everybody.
Bye.
Yeah.
Bye.